Today we are going to discuss rectifier in semiconductor. So rectifier, it is a device that converts AC current into DC current. What is AC current? Here you have diagram of an AC current. This is AC current versus time diagram. You can see that the value of AC current at different times, like at T1, T2, T3, and you will find that value of AC changes. Here at T1, value of AC is having one value. At T2 time, it is having some different value. Now, at yet another time, T3 time, its value is different and its direction also is changed. You can see here. AC was along one direction, positive direction. Then after passing of half time period, here half time period is passed in one complete waveform. The total time taken is capital T equal to time period. Now when half time is passed, then direction of AC is changed. It becomes negative. This is your AC. It varies in time. Not only in magnitude only, it also varies in direction. In first half time period, it is flowing along one direction. In the next half of the time period, it flows in another direction. But here you have DC. DC has a uniform magnitude at each and every time. At T1, T2, T3, you have same value of current you can find. Value of current does not change. And also, its direction is same. Direction also does not change. So this is AC and DC. A rectifier converts AC into DC. It converts AC into a current that has same direction and magnitude also is same. So for that we use a semiconducting device that is called PN junction. So this is symbol of a PN junction. You will see that there are two kind of biasing. When this broad end side of this triangle is connected to positive of a battery, here broad end and positive of this battery, then this combination is called, this connection is called forward biasing. In forward biasing, you have current of the order of milliampere. But in reverse biasing, and yes, this current in milliampere is obtained on a very small voltage. You have to apply only 0.2 volt for germanium, or for silicon PN junction, you should apply only 0.5 volt. So on very small voltage, you have a current up to milliampere, of the order of milliampere. But in reverse biasing, here you can see that when the positive of the battery is not connected to the P side of PN junction, it is in reverse biasing. Then now you have current of the order of this is of microampere, and you have to apply very large voltage of the order of 20 volt or 30 volt. So on high voltage, current is very small. So this current can be considered as negligible. You can consider this current as zero. So in forward biasing along one direction, when current is flowing, then it allows current through it. The semiconducting diode, it allows current through it and circuit can be made. But in reverse biasing, current is very small. You cannot even notice when ammeter is of a milliampere range. So in reverse biasing, we consider that no current flows in reverse biasing. So here we have the diagram of current in forward biasing versus voltage, and current in reverse biasing versus voltage, which is drawn in third quadrant. Here you can see the current is of the order of microampere, and in forward biasing it is of order of milliampere. So, and you can see that this current also is very small, up to 80 to 100 volt. Current is this small in reverse biasing. So it can be neglected. Now, we can consider that when connection is made in reverse biasing, when positive of a terminal of a battery is not connected to P type, it is connected to N type, N side of the semiconductor, then we consider that zero current flows in reverse biasing. Now, for making a rectifier is a device that converts AC into DC. We use the same diode. The same diode I am using here. Here one diode is connected in this circuit. This is half wave rectifier. It rectifies the current only for half wave, not for one complete wave. So in this you can see a transformer is connected. Here you have primary circuit. Here current is fed, AC current is fed, variable voltage is fed, and it is no way connected to secondary circuit. Now, due to change in magnetic flux or magnetic field near to this primary coil, there is induced an EMF in the secondary coil. Here you have secondary coil. There is no mechanical linkage, and therefore why the flow of current will be smooth. Now, in secondary coil, you have a variable voltage just like in AC, but this is in out of phase. Okay, so when voltage is positive at A, voltage is positive and it is connected to P side of this PN junction. So we know that when positive terminal is connected to P side of a PN junction, then this connection is called forward biasing, and in forward biasing this diode, PN junction diode, allows the current through it in forward biasing of the order of a few milliampere. So when this terminal, this point is positive, so it allows current through it, and along with the diode you have a load resistor which is connected in series with this diode. So when current flows through this diode, the same current flows through this load resistor also. And this happens up to half time period in a cycle. But in the next half time period, in the same cycle, when the AC current is reversed, now here you have negative voltage and now here you have positive voltage. So for the next half time period of the cycle, current will try to flow in this direction. Now this diode, which is in this condition in reverse biased, is not allowing the current through it. So here current is break. And so why? The current is also break at the load resistor. Okay, so now the kind of graph you obtain, graph of voltage across A versus time period, versus time, not time period, versus time. So at this point A, which is before the diode, and here you have time varying voltage, because AC which is fed into primary, it is time varying. So the EMF induced in the secondary will also be time varying. And before diode at point A, you have this form of voltage versus time graph. This is sinusoidally varying voltage with respect to time. Here you can see that voltage firstly is increasing in first half time period, then decreases to 0, and then voltage changes its direction. Now at the load what happens? You could see that it is allowing the voltage or current for only first half time period, for which this point is at positive potential. But when this point comes at negative potential for second half time period, it does not allow current. So current also does not flow through this load resistor, and therefore for second half time period, here current is absent, here your voltage is absent. And now when in the next time period, in the second time period, and in half of that second time period, first time period passes, now you have second time period and half of the second time period for which this point is at positive potential. This diode will allow the current through it, and therefore you have current, you have voltage across the load also. But in the next half of the second time period, again the diode is at reverse bias, it will not allow current through it. So now voltage becomes 0. Voltage is absent from here. So this is the graph of voltage versus time of a half wave rectifier. Here you can see, as you know that DC has two characteristics, DC current. First characteristics is that it should be unidirectional. And second, it should be of steady value. Now you can see that at load, at load resistance, voltage has become unidirectional. It is not going to another direction. So voltage has become unidirectional. But it is like making and breaking. Current is switched on for the portion of graph, and then it is switched off. Then again it is switched on and off. So this is one demerit of half wave rectifier. So here you can see that it becomes unidirectional. Voltage is along one direction, it is not along the other direction. But it is not having steady value. there is ripple, there is variation of voltage. Voltage is not uniform. So two things here we see. And one more thing, that when reverse biasing of this diode is done, then one thing we must take into account and consider. So what is that? When you apply voltage in reverse direction, when positive is connected to negative of this PN junction, then a current is obtained of the order of microampere. When you apply very high voltage, 20 to 30 volt, then only current flow. And this current is very small, you can see, and its value is quite small, up to your 80 volt voltage application, up to 100 volt voltage application. This current, you can see how much small, very small. And this is your current axis, and this is your voltage axis. So current you will find this much small. This is your only 10 microampere or so. Very small current. This current is called saturation current. Saturation. And after that, after 80 volt, suddenly with a small change in voltage, current increases to this high value. Current becomes this much. So this current, which is very high, it is due to internal field emission. This phenomenon is called internal field emission. So at junction, you will find that here PN junction, you have depletion layer. This layer is called depletion because it is depleted, it is free from mobile charges. It has not any mobile charges. All the charges are bound charges. Now this bound charges, after gaining sufficient energy due to such a high voltage, reverse bias voltage, it breaks down your bound charges, which generally do not flow. They do not flow. The flowing charges are mobile charges. So these bound charges which are bound, they do not flow, but gaining such a high potential and electric field, they break down, and suddenly a very high magnitude of current starts flowing at a particular voltage. This voltage is called breakdown voltage. So we will try to apply the reverse bias voltage less than this value. Reverse bias voltage should not be equal to this value. You should apply nearly 50 volt reverse bias voltage or 60 volt reverse bias voltage, because when you apply a reverse bias voltage here in this circuit, if you apply a reverse bias voltage of value 80 volt or more, then what happens? You will find that current suddenly increases to a very high value. And you know that Joule's law of heating, Joule's law of heating. What is Joule's law of heating? Heat energy is equal to I square RT. When I increases sufficiently in a very large magnitude, then heat will also be increased to such a large order, and due to that heat your diode will be burnt. So we should try to not let the voltage reverse bias applied voltage be greater than this breakdown voltage of this diode. Diode has a certain breakdown voltage, and applied reverse bias voltage must not come near to the breakdown voltage of this diode, PN junction diode. So these things we must consider. Now you have full wave rectifier. That was rectifying only half of the wave, you can see. This is just like switching on the current, and then after switch off, switching on the current. So it is not useful. And for that we use full wave rectifier. In full wave rectifier we use two diodes, and here you can see there is certain change in circuit diagram also. So from the secondary of this transformer, you have a transformer, and from the secondary of the transformer we connect two diodes, you can see, and then the end side of the diodes are joined together. Here you have connection, they are connected together, and the P side of the diode, here P side of the diode is connected to the secondary terminals of the transistor, both the P sides. Here you have P side, the two P sides are connected to the terminals of the secondary coil, and N side of this PN junction are connected jointly. Now from the center you have a central tapping terminal. Here you have, from the middle of this secondary you have taken a terminal, a end point. What does this mean? Due to earthing, its potential will always be 0 volt. Its voltage will not exceed because of it is earthed. And now by this connection, by the joining of these two diodes, we connect one load resistance in between this central tapping and this joining of the end side of the two PN junction diode. So this is circuit. Now how it works? In first half time period, here I must say you have AC and here you get DC. So AC will be time varying, sinusoidally varying voltage or current, and due to changing magnetic field here in the primary, changing flux here in the primary, there will be an EMF induced in the secondary that will be of varying nature, time varying nature. So it will change like AC. Suppose at any time at point P you have positive potential. So for that time for which point P is at positive potential, you have another, here let me take a point A and B. P is P side, so A and B, okay. At time when A is at positive potential, at the same time B will be at negative potential. So you find that a positive potential is fed to P side of a PN junction diode. So there will be forward biasing. So it will allow current through it for first half time period. And here you have V0, V is equal to 0, and here you have the voltage due to which current is flowing through it. So a current will be obtained through load resistance. Now see what will be the nature of the current. So for first half of the time period, T half, point A is at positive potential and it is connected to P of this PN junction diode. So forward bias, so it will allow current through it. But at the same time, B is at negative potential, so it will be reverse biasing. Negative is connected to P side, and in reverse biasing, as we saw, the current is negligible, 0. So for that time, current is flowing through A, current is not flowing through B. But what happens after half time period? After half time period, now A will be at negative potential because the direction of current changes. In AC for first half time period, direction is if positive, then in second half time period, direction should be negative. So A will be at negative potential in second half time period and B will be at positive potential. Now again current will flow through load resistance, but not due to this diode. Here current is not flowing through this. Now current is flowing through this path. It is at 0 potential and current is flowing through this part of the circuit. So for first half time period, there will be voltage, there will be current through load resistance due to this diode 1. Let me tell this diode as diode 1 and this is your diode 2. And you know that current flows when there is potential difference. It is always made at 0 potential due to earthing. So here is potential 0 and there will be certain potential as per applied AC. So all these things we discussed. Central tapping is at 0 potential. A is positive in first half time period. Then potential at B will be out of phase, just opposite, it will be negative. And diode at A will be forward bias and only it can pass the current through it. When B is at positive potential in the next half time period, now current will not flow through diode 1. Now current will flow through diode 2 because diode 1 is now at reverse biasing. So let us see the diagram. Here you have waveform or voltage at point A. You can see A is before your PN junction. So the voltage will be the voltage of secondary and which is your time varying voltage. So A will have voltage of this kind. It is time varying. At this time, suppose this is T1, voltage has this value. At T2, voltage has increased. And at T3, voltage is reversed. It has changed the direction and it has a different magnitude also. So this is the waveform at A. And at the same time, here when time is same, suppose this is your T is some T1, T is some T1. At T1 time, when A is at positive potential, then B point will be totally out of phase. There will be a phase difference of 180 and you can see the voltage is along negative direction. So these are the two waveforms. at given time in your secondary circuit at point A and at point B. Now, what is waveform at the load? At load, you find that for the first time half time period, current is through diode 1 and it is giving the current in forward direction, same direction. Now, in the second half time period, diode 1 is in reverse bias. Now, current will not flow through it. We know that in reverse bias, current is of the order of microampere. We can neglect this current. Now, current will flow through this arm and circuit will be completed. Here you can see complete circuit. One here and another is from here, from this way. So circuit is completed, so current will flow. And it will be in forward bias. Diode 2 will be forward bias. So for first half time period, current in the load resistance is due to diode 1. In second half of time period, first time period, current in the load resistance, this is your waveform of load. Current, you may say voltage or you may say current. So voltage or current in the load resistance is due to second diode. Now you take second time period and half of that second time period. Now voltage form will be due to your first diode and then due to second diode. So you could see the direction is same. So this has changed to DC halfway. Here you have same direction. Direction is not changing like that in AC. So direction is same. So it is converted into DC. But you can see that there are ripples. They are not uniform or steady value. There are variations. So for that we will use filter circuit. So you will take this complete circuit in a box and you will say rectifier. Here you can see I have taken the complete thing in a box and I have said that it is your rectifier. Now I am connecting a filter circuit. What is filter circuit? Either connect an inductor in series with load. Here you have load resistance, and connect a inductor. Here you have an inductor which will offer some inductance in series with load. It will just suck all these ripples. It will make the current uniform, steady. It will consume all the ripples. So either you connect an inductor in series with load resistance or connect a capacitor in parallel to load. So how it consumes the variations? So in first half time period, in one time period, the first half part of that, the capacitor will be charged. And in second half time period, when current starts reducing, then capacitor will be uncharged, giving current to the load, so that current may not reduce. And this happens in each and every time period. In half of the first time period, it is charged, and in the next half of the same time period, it is discharged, giving current, so that a reduction in current should be compensated by the current of this capacitor. In the first half of the next time period, the capacitor is charged again. Next time period, I discussed for the first time period, then you have second time period, then you have third time period. So after passing the first time period, now you have second time period and half of this second time period. Again the capacitor will be charged. And in the second time period and its last half, it will be discharged and keeping the current constant. So you would be knowing there is a RC circuit, and that is, I am drawing here. Here you have a capacitor, then a resistor. There is a series RC circuit. Similarly, you may have a parallel RC circuit. So in these circuits, when you switch off the voltage and voltage becomes zero instantly, current does not become instantly zero. There is a transient period. So it takes time to, current takes time to become zero. There is some duration, and for that here you have an equation of how charge comes to zero, how charge reduces. It reduces exponentially. So you find that rate of decay is related to this RC. Rate of decay, I am telling you, I am saying you rate of decay. Rate of decay. So the current will be dq upon dt. You will have to differentiate it and then you will find rate of decay. So you will find that rate of decay is related to this quantity, is related to RC. RC is called time constant. Why it is called time constant? So principle of homogeneity you would be knowing. By principle of homogeneity, each term should have same dimensions and units. Here you have charge. Here also you have charge. So unit will be same only when it is unitless. And for that, RC should have unit of time. It should have unit of time. And this is why it is called time constant. So rate of decay is related to RC times constant. And how it is related? You can see here. It is in denominator. So, and with negative value. So when rate of decay is small, so that when rate of decay is small, so that it will remain having the same constant value. It will remain having the same constant value when the current is not decaying, when the voltage is not decaying. So okay, so rate of decay will be small when RC is large. You can calculate this. I am not calculating this time. So rate of decay you can find from here. I is equal to dq upon dt. Then putting the value of I in the equation Ohm's law, V is equal to IR. You can find V, you can find I, and then you can find rate of decay also. And how rate of decay depends on this RC? Rate of decay is small when RC is large. So what is RC? What is R? It is load. You have applied rectifier to fridge. You have applied voltage regulator. Okay, in fridge it is not applied. In fridge we use AC current only. So we have so many devices where we use DC current. And for that we have different loads. We cannot change the value of load resistance, what we have been given. But the value of capacitor in a rectifier can be changed. So for keeping the rate of decay small, we need a capacitor with large capacitance. This decay will be small. This will not reduce when capacitor having large capacitance. So when a capacitor, which capacitor? Filter capacitor which filters, filter capacitor circuit. When a filter capacitor circuit is large, is having large capacitance, then this rate of decay is small. Means current will not reduce. This current change, rate of change is actually small. Better I should write rate of change. Change in voltage, or you can say current also, is small. And we have a constant steady value of DC. Why DC? Because direction is same, direction is not changing. And now you have a constant value also, steady value also. So you obtain a DC, and this DC is near to the peak value of filter circuit. Here you have AC filter circuit current and peak current. Here I should write AC filter circuit. Okay. Here you have filter circuit, input filter circuit. So input filter circuit is having peak at this side, and near to peak of capacitor filter circuit, you obtain a steady value of DC. So I conclude